Today we will discuss about concentration of point imperfections. In the last class we have studied about the definitions of imperfections and what you mean by imperfections, and the difference of the amorphous and the crystalline solids, and what are the divisions of the imperfections. It may be 0 dimensional, 2 dimensional, 1 dimensional, 2 dimensional and 3 dimensional. 0 dimensional defects are point imperfections, and 1 dimensional defects line imperfection, 2 dimensional defects surface imperfections, and 3 dimensional defects they are the volume defects. Anyway, it is the deviation from its regular arrangement of the atom, that is the imperfection. And actually the point imperfection, it is the simplest imperfections involving a single atom or two, and therefore it is referred to as 0 dimensional imperfections. Anyway, it is the missing of the atoms. That is, it is referred to as an atom, that is a vacancy. A vacancy is referred to as that is the atoms from the atomic sites from where the atom is missing. And it is schottky imperfections and Frankel imperfections. Schottky imperfection, it is a type of vacancy in which the atom being free from the regular site, and it may be migrate on the surface of the crystal through successive steps and eventually settles on the crystal surface. Anyway, there is a mixing. In an ionic crystal, however, a vacancy on either a cation or anion site, it must be electrically neutral, that is electrically balanced. That is, equal number of anions and equal number of cations are missing there. That is, this may be achieved if there is an equal number of cations and anions vacancies. Sometimes this vacancy is created or migrate to the interstitial positions, then that point defects is referred to as Frankel defects. See, this is the schematic representation of the schottky defect and Frankel defect. See, here there is a missing of an atom. Here this atom is into the interstitial position, or that is here in the case of the ionic crystals. This is the impurity atoms, and the atom placed in the interstitial position. Here the vacancy pair, that is to maintain the electrical neutrality of the crystal. That is, whenever there is a anion vacancy, there must be the cation vacancy also. This is the interstitial atom, and this is the impurity atom. Here this is the vacancy. And this is the formation of the schottky defects and Frankel imperfections. Here that is, here the atom is migrated from this position to the interstitial position, that is the Frankel defects. But here the atom is migrated from the regular lattice sites to the surface of the crystals, or on the surface of the crystals. But in the Frankel defects, it is on the interstitial position. That is the difference. Now we are trying to go to the theory behind this. Here we are going to find out the Helmholtz free energy. We know that the Helmholtz free energy, that is denoted by F. F is equal to U minus Ts, where U is the U stands for internal energy and S for entropy. And this Helmholtz free energy, it must be minimum in the state of the equilibrium at a certain temperature. we consider the another term, that is the entropy, that is denoted by S, and S is equal to K log W, that we know, where K is the Boltzmann constant and W is the number of the possible ways in which the elements of the system may be distributed. And also in terms of the number of sites in the unit cell, we can also rearrange this equation of the entropy in terms of the number of sites, that is S is equal to K log N, where N is the number of sites in the unit cell. And now we consider here see this equation, NES is equal to N into EH minus EL, and here EH is the energy required to take an atom from the interior to the crystal surface, and EL is the lattice energy per atom. So the energy of formation of the each imperfection, ES is the energy of formation of each imperfection, depends on EH and EL. So we can write this minus ES, NES is equal to N into EH minus EL, where EH is the energy required to take an atom from the interior to the crystal surface, and EL is the energy of the lattice or lattice energy per atom, that is ES is equal to EH minus EL. And this we can also write the internal energy of the imperfect crystals, that is EI is equal to EP plus NES, where EP is the internal energy of the perfect crystal and NES is the this one, that is the change in the internal energy of the crystal. So the internal energy of the imperfect crystal is equal to internal energy of the perfect crystal plus the internal changing internal energy of the crystals, perfect plus change in the internal energy. The change in internal energy is to take an atom from the regular lattice to the surface of the crystals, that is EH minus EL. Meanwhile, we can write this energy of the imperfect crystals is equal to EP, that is energy of the perfect crystals plus change in the internal energy of the crystals due to the atoms from the regular lattice to the surface. Okay, now we can find out the thermal entropy of the perfect crystals. We can find that it is approximately equal to SP is equal to 3NK into 1 plus ln KT divided by H nu. Neglecting the 0 point vibrational energy for H nu very much less than KT. So this is the approximate value. SP is equal to approximately equal to 3NK into 1 plus ln KT divided by H nu. Now we look into these equations, that is S1 is equal to 3nx K into 1 plus ln KT divided by H nu dash plus 3n minus 3nx K into 1 plus ln KT divided by H nu. Before going to these equations, we need to understand a concept, that is in an imperfect crystals, the atoms neighboring a vacancy, if the atoms neighboring a vacancy will have a frequency nu dash, this is nu dash, This is for the vacancy that is very much less than this frequency nu in the perfect crystals. And also it is assumed that in a imperfect crystals, if each atom neighboring a vacancy, it is equivalent to the 3 independent harmonic oscillator of frequency nu dash. That is, if there is a vacancy is present neighboring the atoms, it is equivalent to the 3 independent harmonic oscillator. It is treated as the independent harmonic oscillator of frequency nu dash. There are two possibilities. See this. For a coordination of 6-fold and for a coordination greater than 6-fold. For a coordination of 6-fold or below, NX atoms will oscillate with frequency nu dash. Coordination of 6-fold or below, so the NX atoms oscillate with frequency nu dash. But 3n minus NX oscillate with the frequency nu. Okay, here NX atoms oscillate with the frequency nu dash, but 3n minus NX will oscillate with the frequency nu for the case of coordination number is less than or equal to 6-fold. But the case is different. In the case of the coordination number is greater than 6-fold, what happens? 3nx atoms will oscillate with the frequency nu dash. Here nx atoms oscillate with the frequency nu dash, but here 3nx atoms oscillate with the frequency nu dash and 3n minus 3nx oscillates with the frequency nu. These are only the assumptions by considering the it as the three independent harmonic oscillators. Okay, now we can write this the thermal entropy of the imperfect crystals. This is entropy of the imperfect crystals is 3nx k into 1 plus ln kt divided by h nu dash plus 3n minus 3nx k into 1 plus ln kt divided by h nu. And we can find out from this equation only we can find out what is the case of this. Here nu is, that is 3n minus 3nx oscillates with the frequency nu and 3nx oscillate with the frequency nu dash. So it is understood that this is the 4 coordination number greater than 6-fold, that is the case 2. Now we substitute our previous equations, that is this one. This Sp equal to 3nk into 1 plus ln kt divided by h nu, where Sp is the thermal entropy of the perfect crystals and here is the thermal entropy of the imperfect crystals. Now we can find out the change in the thermal energy, that is delta S equal to delta S suffix th equal to S1 minus Sp equal to 3nx k into 1 plus ln kt divided by h nu dash plus 3n minus 3nx k into 1 plus kt divided by h nu minus this term, that is 3nk into 1 plus ln kt divided by h nu, and finally we will get this equations, that is nk ln nu divided by nu dash whole raised to 3x But if we consider the case 1, we will get the same equation, but it has all raised to x. Not see this difference. So, this is only by considering it is as the independent harmonic oscillator. Okay, this vacancy is considered as the independent harmonic oscillator, and that is vacancy in connection with the neighboring atoms, or the atoms neighboring with a vacancy. Both are correct. And it is considered as the independent harmonic oscillators. There are two cases: coordination number less than or equal to 6, coordination number greater than 6. Now we have to find out the possibilities. That is the number of ways arranging n identical vacancies, small letter n, for the vacancies, and capital N is for the lattice sites in the crystals. So, the possible ways of arrangement is WEF is equal to n factorial divided by n minus n factorial into n factorial. And the associated the associated entropy is KLN. W is equal to KLN n factorial divided by n minus n factorial n factorial. This is that is the entropy associated with this. W is obtained from the Boltzmann equation. Now we are going to find out the total entropy, that is S is equal to STH plus S, that is the sum of the thermal and configural entropies. The total entropy occurring in the usual thermodynamic formulas, that is equal to S is equal to the sum of the thermal and configurational entropies. That is, this is the thermal entropy. If it is case 2, this is all raised to x. Sorry, if it is case 1, this thermal entropy is in the power of x. If it is case 2, this thermal entropy is in the power of 3x. And this is the configural entropy, that is SCF. So, now the total of the entropy is equal to the sum of these two, that is STH and SCF, that is the configurational entropy. And now using the above equations, we can also find out the free energy of the imperfect crystals. Free energy of the imperfect crystals, that is F is equal to EF plus NES minus this terms and also minus this terms. That is, our equation is Helmholtz free energy F is equal to U minus TS. We find out the entropy. This is the total entropy, and this is the internal energy. So, F is equal to U minus TS. Now, we apply the Stirring's approximations to find out ln x factorial is equal to x ln minus x. For x is greater than, very much greater than 1. So, we can write this terms, that is ln n factorial divided by n minus n factorial is equal to n ln minus n minus n ln n minus n minus n ln, by considering this law, that is the Stirling's approximation. Ln x factorial is equal to x ln x minus x, and you have studied using this n factorial, that is I think that is better to remember. Ln n factorial equal to n ln minus n, that is easy to remember. Applying these equations into these equations, we will get this term. So we can apply this ln term into our equation number 10. We will get this one. And if we differentiate this into dou f by dou n with respect to n, we will get the equation is n by n equal to nu divided by nu bar whole raised to 3x exponential es minus kt, where n is very much less than capital N, where capital N is the lattice and n is the our vacancies. Okay, and this is the case for if we treat the case 1, that is coordination number is less than or equal to 6. See, here it is power of x, but if we treat greater than 6, we get the power is 3x. And this is the table that shows the enthalpy formation of vacancies of some crystals. This is the shortcoming of this, that is R is equal to nk. Substitute, we will get the value of universal gas constant, that is 8.314 joule per mole per Kelvin. Okay, and these equations is very much equivalent to our relations that we studied in our thermodynamics class, that is n by n is equal to nu divided by nu dash whole raised to x exponential minus delta h divided by kt. And this is the schematic representation of the energy, configural entropy and free energy in terms of n divided by n. Energy, configurational entropy and free energy term. And with respect to as a function of n divided by n, that is the ratio of the vacancy to the lattice. That is for example, suppose that in a perfect metallic crystals we produce a certain number of vacancies by transferring the atoms from the interior of the crystal to the surface. That is transferring atoms from the interior to the crystal surface. That is the Schottky difference. This will require a certain amount of energy, so that the internal energy of the crystal will increase. The internal energy of the crystal will increase. As a result of this, that is as a result of this increase in internal energy, the free energy will also increase. That is this is the free energy that will also increase. But our equation F is equal to U minus Ts. So the increase in the internal energy, which is unfavorable in the thermodynamical sense. On the other hand, creation of vacancies increases the disorder in the crystal, which in turn increases the configurational entropy from 0 to a certain value determined by the number of vacancies n produced. Since the entropy appears in the expression, that is F is equal to U minus Ts, there is the entropy is first decrease and then increase. As a result of this competition between the internal energy and entropy, the stable state of the crystals will always contain a certain number of vacancies. And see this figure, there is the schematic representations of the energy, configuration entropy and free energy. The equilibrium corresponds to the minimum value of F at temperature T. You must study this derivation, that is a very important derivations. I hope you understood these derivations, and I will give the copy of the scanned copy of the same to the Google Classroom. Okay, thank you.